And we'll put the presentation in the Telegram as well, just so you can follow along and see everything.
All right, hi everyone. I'm going to be talking about EVM evolution, which is sort of a larger program to improve the EVM, kind of mature the execution engine that we have today, and kind of do incremental improvements so that we can show progress and ship some stuff faster. I usually start presentations with a couple quotes. So extinction is the rule, survival is the exception, and evolution is about looking forwards. So a little bit about this talk, in brief. So my name is Zelenka. I'm XP'd everywhere on the internet. I'm the CEO and chief scientist at Fission. I work with Boris. I'm a programming language theorist and VM enthusiast. And I'm listed as an author on a couple EAPs. The one that we'll be touching on today is 615 subroutines and static jumps, primarily Greg Colvin's work, but I'm a co-author on that one too. So why even care about the EVM? It is critical infrastructure for the future world financial system, plus all this public compute that we do. But the current design and the original design leaves a lot to be desired, but it's also not going away. So there's currently no hard EWASM date as far as I'm aware. My guess is maybe not Istanbul, unless somebody wants to correct that, I'm not sure. And it's also used in more places than Ethereum mainnet. So this group probably mostly cares about mainnet, but there are large companies using this as well, or people running it on sidechains, etc. So it's not going away. There will be more effort being put into it regardless. So it would be probably a great idea to keep it improving. Goals from this presentation. We are not the only game in town. So how do we survive as Ethereum to see ETH2? Right? It's probably not a short program. We're not going to see ETH2 in a couple months. This is an EVM-friendly vision of the future, or somebody called it yesterday, grand vision for moving the EVM forward. And this is forwards compatible, so maintaining compatibility towards EWASM. Right? So this isn't an or, this is an and to inspire more effort in this direction. Goals from the project are to make things incrementally deliverable so that we don't have to do it all in one big shot, both hard fork and non-hard fork changes, mature the platform, the spec, and how everyone else is writing their implementations. So the main complaints are speed, tooling, and language support, and we think that we can solve all three. Reduce runtime and hard fork bugs with better analysis. And again, keeping this all forwards compatible. So current timeline looks something like this. We have now and sometime in the future. And somewhere in the middle here is EWASM. And the theory is that suddenly we're going to have, everything's going to change, everything's going to be better, which is great. But what if we can move some of those up a little bit sooner? And we can do some of these changes. Now, this is obviously a simplified representation, right? But we can do some of these changes without having to change the spec, and some of them do require a hard fork and this hard dependency between them. Those dependencies look a whole lot like this. I realize that's probably very hard to see in this bright room, but the slides are going to be posted online, or they might already be. Yeah, they're in the Telegram. And these are also posted to Medium and Fission.code's EVM evolution article as well. There's very few hard dependencies between these pieces. The big one is static jumps, which is that top sort of middle one, is dependency for subroutines and deprecating dynamic jumps. So that's deprecate, not remove. And we'll talk about that in a little bit more detail. The rest of the dotted lines, which again from the back might be hard to see that they're dotted, are things that enhance each other but don't necessarily have a hard dependency, so you could ship those together. This is going to be broken into 5 sections: safety and structure, raw performance, WASM transition, and platform maturity, followed by Q&A. All right, So let's dive in, safety and structure. We have some special concerns being on a shared platform, right? We have control of assets, which makes this a high-value target. That's going to be no surprise. But even the optimization passes that we do on a client are now susceptible to attack, right? If they take too long, somebody can use that to grind the network to a halt. So we have to keep things as close to constant time as possible, which is a high, it's a tall order, but we can get fairly close with a lot of things, especially in the way that we design them. The three big issues in this first part of the roadmap, and there are absolutely further things, IO-bound stuff we would love to tackle, but we're dealing with low-hanging fruit at the moment, so unstructured flow, modular arithmetic, and non-totality. One of the big questions we get with all of this stuff is why should people even care about static analysis? If you have contract invariants or properties, which I believe is the talk after this, so that'll be a nice segue, you can check that the code behaves correctly. The better analysis you can do, the more that you can say before you run the program if it's actually going to do that thing, which is very important when you're dealing with large amounts of value. And we can eliminate entire classes of bug. We can remove runtime checks, which improves performance because you're not doing as many runtime opcode execution. And we can improve JIT and ahead-of-time compilation. There was a larger JIT project a while ago that was stopped, and I'm not sure entirely why. If anybody knows, I would love to hear more after, but that helps with both speed and other kinds of optimization, memory, etc. Unrelated to Ethereum directly, but Microsoft published a couple months ago this graph. 70% of all of their security issues were memory safety. And they were able to add some more tractable static analysis to their platform and took that 70% to 0. So with analysis, we get both safety and optimization. So starting with structured flow, which is just the paths through the smart contract. This is the main focus of EIP 615, which is deprecating static jumps. Well, I guess we'll go into this in a moment. So we get faster interpretation immediately, and transpilation to EWASM is easier. Because the structure suddenly of the EVM opcodes now match much closer to what WASM has. We get better compilation from other languages because of what we expect to see in an ISA. Easier static detection of exceptional paths, so you can check with your tooling that things will actually run through as opposed to hit some exception. We can determine allocation bounds because it's a clear idea of what's going to happen when we execute. And we can do much, much, much more aggressive compilation. We can use appropriate sized registers, do gas aggregation, something that the WASM team is looking at for their project as well, and do it 100% in client internals, don't have to adjust the spec after these changes. The strategy here is deprecate dynamic jumps, so that's not to remove them. That's just say, Solidity shouldn't compile with dynamic jumps going forwards. We introduce subroutines, disallow bad control flow and stack use that would be dangerous, and do this, and again, from the design of 615, we can do this in quasi-linear time, so n log n, which is specifically to guard against those attacks. And is fully backwards compatible because we're not removing anything or changing anything, we're just adding. These are the new opcodes, there's 10 of them. Some people don't like that there's so many. We could ship these in smaller batches. That would take longer, and you really get the benefit with them when you do them all together. Actually, yeah, so it's essentially replacing jump functions with ones that you have to provide a specific address to ahead of time at compile time. Subroutines, and then this get input local at the bottom are both for, we end up with stack frames. So that's local variables.
Question.
Yeah.
You said this laptop lets control flow stack use. Are any of those on mainnet currently?
The argument for speed, it doesn't come straight out of this work directly. You would then have to optimize. But because of analysis, you can start removing checks that you don't need. So as a really simple example, if you have a check early in a program that something is going to be a multiple of 4, you don't have to check if it's an even number later. You can pull those checks out, right? You can say, I guarantee that this is in these bounds because I've already done this check. So we can start pulling things out and do other kinds of analysis too. Because we have this clear CFG, we can simplify the cost dynamics, which is a fancy way of saying simplifying gas metering, doing aggregation of that. And we'll look at that with a simplified example in a little bit too. And then optimization. So we can do rewriting theorems, inlining, tree reduction, concurrent execution of both separate smart contracts, as long as they don't have a dependency between them. So again, we have to understand the graph, right? Between different contracts, also inside a contract, and that will flow very nicely into sharding when we have that with ETH2. What that looks like is essentially this. So this is sort of the classic sort of dependency graph. So we have a partial ordering of this basic arithmetic, right? We're doing 11 plus 9 times 2 plus 4. We can split those up and do them in parallel. Overflow avoidance, so for safety in particular, we have a couple options, bounded or fixed arithmetic. So add a couple opcodes that have, that are essentially safe math, but at the VM level. So you don't have to do all this extra checking, right? Advantage, no manual checks happening. Languages can just compile with this directly in it, so you'll have it by default. You can bound things around enums, higher level constructs. So you say, this only has 3 elements in it. This will be bounded to 3 elements, which is, paving the cow paths, right? Instead of having to require or, pull in safe math, use that for all of your arithmetic. Now it's just automatic. It's built in. The disadvantage is you need to add some more opcodes. Option 2, which I believe was mentioned in a thread by Nick Johnson, is to add a carry flag. So it's flexible, backwards compatible, but you still have to do these manual checks, and you have to add a flag to the VM. So if you're going to overflow or underflow, you set this flag, check for it, and then do your error handling there. And total contracts, Turing completeness considered harmful. Something that people have sold Ethereum with is that it is a Turing complete system, except that it's not, right? We have a limited runtime, you have a gas limit. We don't want things to run forever, and that's really the distinction of a Turing complete system versus things that aren't, is that it can run forever, right? So smart contracts have a limited runtime, must be completed in a block, deterministic, and costly bugs. Turing complete systems, yes, they can compute anything that is computable, but that also might take 100 million years to do. We don't want that, right? You can do infinite loops, and then we run into the halting problem. If you remove a few things from a Turing complete system, it stops being Turing complete, but you also eliminate the halting problem. So just like the structured control flow from earlier, we can have just generalized structured computation and prove a whole bunch of stuff about it. That all inputs have outputs, so we don't have any bugs in a program. You do this by showing that a program is made up of only total components. So you don't have things like unbounded loops, so a while loop that can go forever, it must have a counter on it, for example, right? For loops are okay. You can iterate over arrays, etc. And we can then check not just that it will terminate, but in how many steps or some range in which it will terminate. So we can do essentially a big O of how quickly this thing will finish, which also helps again with gas. And this is also possible with external contract calls if those external contracts are also total. So we can have full compositionality. Section 2, raw performance. So these are some practical options. They don't really require hard forks for the most part. There's a couple instructions that I'll touch on briefly. So issues here, clients are primarily running interpreted VMs, which is very slow. We have a naive gas calculation per opcode on average. 256-bit words means that we have to do a number of instructions just to do, say, addition, which should be just a single machine instruction. And we have a lot of missed opportunities for concurrency. So how do we speed things up? There's the hard fork and the non-hard fork version. Doing explicit SIMD and dynamic word size regions are options to improve math and common operations. Or again, using analysis, we can do gas aggregation, check for regions that don't need the full width of 256 bits, so that we can do them natively. Implicit SIMD, if we're doing something that looks like it is parallelizable in that way, we can do that. MIMD is kind of a question mark after it, whether or not we'd get much value. TCO, and of course compilation, down to native code. So the easiest way to do this is you take the EVM instruction set as it is today, read it in, and turn it into an optimizing IR, something that is better for analysis. So you lift it from this very, very low level thing up a level, do some analysis on it, understand how it works, and add a little bit more information back into it. So we can call this something like EVM Prime or ReVM. There is a project called Slither, which is more for analysis than for speed. So this would be aimed more at the speed benefits. So to make this progressive optimization, so we can do multiple passes on it, make it faster and faster each time, and do some very, very aggressive optimization. Decouple that gas metering, so instead of having just instructions, pull the gas parts out, and then do optimization on that. Do dependency analysis, so we can do concurrency, and then again, that helps a lot with sharding. So diving a little bit deeper into native word size. Obviously, this is a huge number, 1.3 some billion, I believe, which today has to be emulated. I'm not sure that there's a single piece of commodity hardware that has 256-bit registers. And it's actually easier to do the other way around. So if you have 4 64-bit numbers, you get the same thing back. For most of what people are doing, as far as I'm aware, on the EVM, it's with these smaller numbers. It's much rarer that we need to construct these larger values. So it actually makes sense to start looking at things from the native word size and then emulating as we need to, rather than always emulating and throwing away this lost work. So explicit regions, we can add an opcode with a word size flag. Say, for this stack frame, for example, this will be in 32 bits. So we give a frame width opcode, set number of bytes. Option 2, which is I think a little bit more interesting, is you can deprecate, add a multiply, add some more modular ones, and set some new static forms around modular arithmetic. So switch to add mod 32 or 64 for all math, and then do optimization passes. So for example, in this one here, we have add mod 64, subtract, add mod 32, 32. We know that we will be in 32 bits. So we can drop the rest of the 256 and just stick down to a native word size. Defensive JIT, speeding up contracts on these adversarial systems, is a fairly straightforward, I think, way of doing this. So today, you have your contract state and the contract bytecode that is deployed, which is essentially a ROM. And the proposal here is to add optimized code as a point as well, and then a keep optimizing flag and the last optimization ID. And those don't have to be kept in the state tree or anything. That's just per client as an optimization. So if this is time 0 to time n, Everything above that line is the end net result, and everything below is the optimization happening in the client.
Sorry, quick question.
Yes.
How can you do that outside of consensus?
Because the semantics of the contract are the same.
But aren't the miners who are running the optimization getting a significant advantage in mining?
Yes.
So isn't that going to increase the uncle rate significantly?
So the end result of running the program is the same.
Right, but the miners who have to run the program now, they're not all going to be running the same optimizations, right? It's not deterministic.
Yes, so they'll be incentivized to run optimization to keep up with everyone else.
Yes, but they're not going to run the same ones. That's my point. So they're not going to have the same, you're going to have like different networks effectively.
Well, same thing today with Geth, Parity, Trinity, etc., right? They have very different performance characteristics already.
And that's already a problem, yeah.
Do you want to highlight what basically what's the impact there?
Oh, I mean, it's just going to increase the uncle rate. I sort of assumed this whole talk that you're talking about stuff that would run during like the Solidity compile, right? That people would be submitting new bytecode to, or somehow passing in via some side channel or something to the miners the optimized code, so that we could have consensus on that code. I assume also like your optimization paths are going to be non-deterministic, right?
No, they're deterministic.
So if they're deterministic, that helps a lot. But they should probably still be gossiping to get agreement on the optimization of a given contract.
I mean, they can do this literally today, right? The idea is that if you have, take a simple example, 3 additions, and you're doing those interpreted, versus you compile a binary that does this addition, the end result is the same. So it's as if you bought a faster chip.
I'll have to take this offline. But that I don't think that addresses, in making this proposal, you're suggesting a change in the relationship between the various miners.
I mean, again, they could literally do this today, right? There's nothing changing in the network at all.
Okay.
Yeah. We'll talk about it after. Anyway, so above the line is the net result. Everything below is optimizations happening on the client. We will always keep the original interpretable bytecode and then start running JIT passes. So we need to get amortized gains. Running the JIT pass is computationally expensive to some degree. So we need to prove that this is something that is going to get us some benefit to do that work in the first place. So after some number of passes or some number of calls, let's say this is CryptoKitties, which gets called a lot, then you start your first pass. And if it succeeds, you cache the JITted code and say, okay, for this next period of time, that's what I'm going to use. Same thing for the second pass. We'll have the second one here. And then we try the third one, and it fails within some particular amount of time because these happen. We now have a Turing complete program trying to do optimization, right? So it might take longer than the window we're going to allow. We stop that. We record, this is the last one that we tried for, and this second JIT is used for the rest of the lifetime of the client. Gas metering aggregation, so doing cost dynamics. We can decouple, as I mentioned a little bit before, using that IR pass. Split out the gas calculation, do some control flow analysis, reduce the actual calculations, and then any of this research can be shared by the WASM team and vice versa. So here's a simple, quick example, right? So we have a couple of pushes, a lesser than, a push of an address, a jump, and if there's no jump, this will end up as 25 gas, and if there is a jump, it'll be 30. We do quick CFG, so I have the tree. This is a super instruction of all of that together. So we have an if less than, where we know that we have this dependency suddenly. So we can actually jump up to the less than, and as soon as we see that instruction, we know based on the two instructions, the two things on the top of the stack prior to it, we will either have 22 or 30, and we can eliminate all the gas calculation after that point. Or another way of seeing this is it's a function from the two inputs to the amount of gas that we'll take, the relationship of those two. And you can generate a function separately so that on function call and the arguments being passed in, for example, you could calculate this immediately. So as a one step. The EWASM transition, so making a switch to the next smart contract engine. So goals for EWASM: speed, tooling, language support. We can look at the architectural similarities between the EVM and WASM and try to bring them a little bit closer. So they're both stack machines. They're both quasi-deterministic, right? WASM isn't fully deterministic, hence EWASM. And so we can do some EVM changes now to make the migration easier later. So this is a table Greg put together of WASM and EIP 615 opcodes. So now we have an overlap of not just, basic arithmetic and stack pushing, but also of these control structures as well. So we can make them identical and make this much easier, do automatic translation of WASM code to, EVM to WASM code, et cetera, so that people don't have to go and start redeploying their contracts or run a EVM implemented in WASM as a precompile or something. Which, by the way, I would love to pick WASM team's brain on that stuff later to know what the plan is for, or if any changes have happened in the transition plan since Stanford. So remaining opcode space for this kind of thing, I mean, we have quite a bit, right? In the cryptographic section, which is 20, we have 1 right now, and then C, D, and E are totally blank. And then we have a whole lot in B, which we're proposing to take up with EIP 615. So there's room to play with still. So this is that accelerated timeline from before of just the features we can get. Let's look at language support, which in WASM is provided by LLVM, low-level virtual machine, which is neither low-level nor virtual machine, but it's a compile target for languages that can then separate out and do backend for. So eventually, WASM will have direct native compilation from, say, Rust down to WASM. These days, they're using LLVM to get broad language support. Right? So that's how all of that is done. And LLVM is also nice because it has a lot of optimization and analysis, and there's an entire tooling set out there that we can use as well. There's nothing stopping an LLVM to EVM backend. So that's the architecture I was telling you about before. So you can take, Fortran down to the common optimizer and then output EVM backend. And you can also compile down to x86 and run it locally on your laptop, any of these targets, right? So you wouldn't even need to, while doing local testing, run it in an EVM if you didn't want to. You could just test your functions normally. The big advantage here is that you can start using all of these languages today, and that's not to say that it's a small amount of work to do this kind of a backend, but if we were to do one, you'd have all of these languages plus more, and then any contracts we write with those today will continue to work on EWASM. A pluggable VM. The VM choice itself, strictly speaking, is orthogonal to the rest of the system. We should have some standard spec definition that clients implement so that they can become pluggable. We shouldn't have to do a special new VM for every client, right? That's not to say that we should only use one VM, but it should be more pluggable so that we can ship better VMs around and have them just work. So standardize the interface, modularize, something probably the entire client could probably use. yesterday, Run EVM, there was some discussion around Canto about doing this for the networking layer, which I think also makes sense, but that's separate from this talk. And you could also plug in non-VMs, right? So you can use, plug in a JIT compiler or compile down to WASM and just put the binaries in directly. So what we could do as kind of a larger thought experiment is you could turn every contract, compile it down to native code, and plug that in as a metered precompile at the client level, not at the spec. Platform maturity in general, so making this more industrial strength. In terms of process, we should be keeping the client spec ahead of the hard fork schedule, right? The yellow paper is out of date, the beige paper is out of date, the jello paper is the closest thing that we have currently. And that's because the work was put into it more recently. So we, as a point of process, I would very much like to see it be, well, actually I have a little thing here. So we also ideally get a spec-generated test suite as well, which is entirely possible. So EIP process finishes, we have it accepted, we update the spec. Ideally then we do any validation that we need to do on it, generate a test suite, generate tooling, etc., and then implement it. I've proposed on ETH Magicians a while back moving to the Jello paper as the canonical spec because currently the closest, fullest spec that we have, it doesn't include the entire client yet. So it could literally be a matter of going into the yellow paper, pulling out the EVM section and saying, look at this part of the spec here. Because again, all these pieces are orthogonal. It doesn't have to live in one big spec, or we can do an incremental takeover of the entire spec. So start building out the networking components, et cetera, in K semantics, generate a spec out of that. And then in addition, we also start getting tests for free. They can do test generation for all kinds of use cases. And we can also do pretty printers of the Jello paper. So one of the main complaints is the notation from K. People find it unfamiliar. Those with a background in formal semantics would find it more familiar, but we can also take it and turn it into the yellow paper notation. There's nothing stopping us from doing that. It's fairly straightforward. It's not no time, but it's entirely possible to do. And same thing with the beige paper. We can make it look like that too, but have the spec be complete. And now we update one spec, which is also executable and testable, with inline comments, and generate something for formalists, something for implementers, and something for curious community members, all in one go. So the broader case for K, we have this higher level spec. It generates a prover and a generator, which gives us code, tests, and docs, all from the same high level spec. Further with specs, so talking about all this optimization stuff, if we develop specs for how to do this optimization, various clients can then go and implement it. And that levels the playing field for all of them. And yes, it's a little bit more work for them to do. But it shouldn't be a client implementer's job to go and think about how they're going to optimize all of this stuff and do this, kind of broader, tricky, JIT compilation. If we can write down how to do that, then people can go take that spec and implement it. While we're at it, we may as well modularize and multiplex the client design. And ideally, and we've heard interest from, especially in enterprise, interest in having a formally verified client. So there is K EVM currently that has this, but that's just the VM. So doing the full client. And then one, specifically we've heard interest for Idris or F-star versions as well. Because right now we have a version in, say, Python, and we're not even sure that it runs correctly. We have tests, which are nice. A fixture test, so when you say pass in these values, expect these back out, you're testing one value for huge space. If you do prop testing, which does automatic test generation, you're saying for some number of cases we have this, but if you have a formally verified spec, it is for all, it's universal, right? I guarantee you that it behaves this way all the time. So looking at that dependency graph again, just to sort of wrap that up. Again, the only two actual hard forks in here, requirements, is static jumps is required for subroutines and deprecating dynamic jumps. The rest of these can all be shipped, or sorry, those three have to be shipped as a package. Everything else is either enhanced by that work, enhanced by each other, and can be done in successive hard forks, the same hard forks, or with no hard fork, depending on the exact item. And again, I realize it's really hard to see that in this bright room, but the slides are currently online. Thank you. And yes, I have 10 minutes for questions.
It's how I'm going to get my exercise.
I actually just wanted to redirect a question you said earlier about what happened to EVM. Was it EVM JIT was the thing you were thinking of? And
Yeah.
I don't know if Pavel wants to answer that.
Not a lot of people were interested, and I didn't have time to keep it updated. So that's the end of the story. It died off after, I think, Byzantium hard fork. So it works up to the previous hard forks. It hasn't been upgraded for Constantinople, but there's a lot of things we can do there. Definitely, it's rather some kind of prototype, not something I would recommend for daily usage.
Could you also comment on the difference between EVM 1 and EVM JIT? Because there was also an experimental quote-unquote JIT VM in Geth, but from Felix's explanation, it was actually more like what Pavel's done more recently with EVM 1.
So, EVM1 is some kind of new EVM implementation, but I just used some knowledge about from EVM JIT so this is something you presented and proposed, that you can actually calculate gas cost in batches instead of trying to increase the gas counter for every opcode. And it's one of the, I think, let's say, 3 innovations EVM1 has. So it just calculates gas cost more efficiently by doing some kind of upfront analysis, which is also required by the spec. So, and well, 2 other things is a bit different interpreter design, but I don't have any numbers if that helps in terms of performance. And the third thing is we just use a bit more efficient big number implementation for the limited big number precision the EVM requires.
It's about 10 times faster in our recent benchmarks compared to, say, Geth and Parity. But so what's the difference between that and EVM JIT?
Well, EVM JIT mostly uses LLVM as a execution engine, so it transpiles to LLVM IR and then generates machine code for the architecture it's running on. It's nothing really complicated there because LLVM has somehow exposed API for implementing JITs. They haven't considered that as something, I don't know how to put it. I mean, it was for a long time also kind of toy API for some examples and so on. But as I've seen it progresses a lot over time. And from recent additions to LLVM, they even make the API allows concurrent usage of that, so we can do JIT compilations concurrently, which wasn't available. So yeah, I guess there are some users in the world that using that, although I haven't in particular identify any bigger project that they use that. Definitely web browsers doesn't use it for speeding up JavaScript compilation. So yeah, I can answer more questions about that later on if someone is interested.
Questions? Or over to the Rick show. I think that just the point is in a bunch of stuff that there's bits and pieces of this. You know, what Brooke is saying and what we've said with EVM evolution is that there's increased interest in improving the EVM. So let's form a working group. EVM evolution isn't versus WASM. It's we have EVM today, we can improve it, and we can move it into WASM as well. Fair? As a statement of, and that there's existing pieces that we can build on top of, right? Awesome.
So I'm going to reduce my questions into categories. So how much static analysis have you done of the existing code in your analysis? I mean, this is a expansive 177 slides. I mean, you've described a lot of stuff here. How much analysis did you do of the existing contracts in making some of these decisions?
Not to the same level that Alexei's done in his work. This stuff is all bare bones, basic, super low-hanging fruit, uncontroversial stuff in any other context, right? These are the basic optimizations you would run on any VM, modern VM today.
Okay, so that actually leads into my next question, which is, and maybe someone in the audience, or maybe you know, but my understanding of what causes the network to fork historically is if we were to implement these types of optimizations as an opt-in, you would be increasing you would almost certainly be increasing the uncle rate, and you would also then be increasing the likelihood of certain types of forks. If you are if you're not analyzing the network to know the impact of these optimizations, it seems as though running these kind of optimizations on an opt-in basis would increase the likelihood of network problems.
So potentially, but again, it's also opting in with running a client yourself on AWS versus with an ASIC versus all these other options. So you can do this with hardware, you can do this with software today, you can, Trinity is not as efficient as Parity, right?
Well, and I'm just sorry, just to chime in, because I don't know how many other people in the community actually analyze this stuff, but some of those clients are just literally not competitive. They're not performant. They don't mine blocks, yes. Right? So, to your point, I mean, you're absolutely correct. But the problem is then those clients aren't contributing to security, and that client diversification is more of a hindrance than a help.
Yes.
And so, I mean, you obviously have done an enormous amount of work, and it seems very high quality. I'm not an expert, but I'm just, to me, from a safety perspective, it would be great to do all of this work, mm-hmm. and then say, look, we have this vastly improved, we've left the 80s. Here we are in VM world. And get everyone to opt into that en masse, as opposed to, and I think that would actually be fairly easy. The other thing, so I'm sort of I'm not making a mountain out of a molehill, but I think part of the problem is that the miners don't actually care. So if you just gave them the thing, they just use it. So I guess maybe that's what I should have started with, is I think that you're making it optional is actually more dangerous and more risky than just making all these changes, giving it to everyone, and then just saying use it.
Yeah. So, I mean, I don't disagree with you. The nuances that I would put on it are, say, let's just take Trinity as an example, because it's not intended for hardcore mining use cases. It's primarily education and as a living spec. It's not competitive with, say, Parity or Geth in terms of speed. it's not competitive. So if we were to release these changes into a client, other clients would have to implement them as well to also remain competitive, because you'd have something that is an order of magnitude more performant suddenly, which is a massive gain, at least at the VM level, right? For the miners, it makes sense too, because now you have a much lower resource usage on your machine, and you can do more mining, and you could even free up space to do mining on Bitcoin or something else too, right? So you can now, with cheaper hardware, do more, or the same hardware, do even more, right? So there's an incentive for them as well of, I'm using fewer cycles, I can get more done more economically.
Yeah, to add to that, having a faster opt-in, I mean, you can't really force everybody to run the same client or the most optimized client. Where the problem comes is when we adjust gas costs, and then so if do a hard fork where gas costs are repriced, and then if they're repriced below, you know, say what the parity client runs, which is why, you know, in Constantinople it was proposed to make the elliptic curve pairing like half priced in half, but parity didn't have the same optimizations that Geth did, so that proposal was rejected, and so now the EC pairing is still the same price. But does the fact that Geth does EC pairing a lot faster than parity, does that create issues on the network now? No. So I think if one client is a lot faster than another, it's not necessarily a problem. It just depends on what the, you know, as long as the gas is still calibrated to like the slowest client.
And that's sort of my point, right? Is that if your solution to the difference is to keep the gas metering at the slowest client, then what did the optimization really do, right? And I mean, I think that's I think that's a pretty hard question to answer, actually. So,
So as someone who understands exactly nothing about economics and pricing, one option you can use to incentivize people to make it faster is to take, say, the 90th percentile, not the lagging ones, right? And say, cool, we'll price it against what 90% of people are doing, and everyone else either needs to go away or improve or deal with the gas.
Yeah, I mean, I'd love to take this conversation offline. I think the optimizations, I think overall, the concept is super important and super useful. I just think that when you talk about not even necessarily the politics, but the practicality of deploying it, given that I don't want to just rip on miners all day, but they're not really paying that much attention. So, you know, I think deploying this stuff is going to need to, ironically, I think it'll be much easier to do these optimizations than it is straightforward for how you deploy them.
Yeah, and I think, you know, there's a whole set of these things which aren't necessarily interlocking as well. So that's the thing. Like, yes, that's a ton of work. That's basically Brooke going, here's 117 pages of what's on my mind right now of bringing the VM into the 80s and which of them are most realistic to roll out. And absolutely, I captured your thoughts on we have to do large-scale contract analysis on a bunch of these things, right? Like, that's the next work to be done. There's a plan. Who can help work on it? How do we split into working groups? So we went up a little bit over time. We're going to keep trying to switch this off. Brooke, if you can grab a table in the next room, or I think you're probably going to stick here for this invariance talk. Yeah, Wei. And so I think really this working group is really the VM working group. So tomorrow with EWASM, after EWASM is presented, that will be really this topic, and along with EWASM and the longer discussions of things. And you're welcome to grab a room whenever you like as well.